Hi, now let's look at some of the data processing techniques. And there are basically data processing has evolved so much over last couple of years, or maybe in last one and a half decades, that there are new pipelines, new engines that come up every couple of years. So we will take a look through this journey. We'll look at how the most naive uh, processing algorithms can work. Then we'll take a look at Mapreduce, which was a great improvement over the naive way of processing. And then we'll take a look at Apache Spark and Apache Kafka Stream, which are two very popular data processing engines in the use today. And then we'll complete the picture with our search and industrial AI use case. So let's start diving in. So broadly, data processing is of two types. There is a batch processing and then there is a stream processing. Batch processing, as the name suggests, it essentially loads a batch of data and then does some processing on top of it. So for example, if you are training a machine learning model, you can think of that as an example of a batch processing, wherein you load large amount of data set and you train your model. Versus when you deploy a model, that is an example of stream processing, because when you are deployed the model, you want this model to act on every data that is coming as a stream and then produce some output based on that stream processing. And in stream processing, there are two kinds of approaches that mostly are followed and very popular. So the first one is a true stream processing, and the second is a micro batch. So what happens in micro batch is that as the stream of data comes in, so that stream itself is buffered, and then it becomes like a small batch, and that batch is what the processing engine operates on. Now these batch sizes, etc., can be determined by the application programmer. They can be something as small as, let's say, a couple of milliseconds or seconds to a large batch size, which can go up to maybe 5-10 minutes or even larger. So what's the naive way of processing? Well, the naive way of processing is that you have your application that is generating your data, then you have your web server that is capturing those data from the client application. You put them in some sort of a queue, and then you have a single process consumer that is taking each message individually and then performing some processing on that message, and then let's say it's storing those processed messages or the outcome of that processing. Now a single process consumer can take you only so far, because if your queue size keeps on increasing or the messages that you are getting is a lot, then clearly what will happen is that you will start to build up lag in the queue. There will be a lot of unprocessed messages that are there, and your single process consumer will not be able to process all of them in time, and hence the entire system starts to get slow or laggy, as it is called. Now one very obvious improvement on top of it is that you can have a multi-process consumer, wherein within that same program you are spawning multiple processes, and each of those processes can also spawn different threads, and hence you achieve some sort of a parallelism, wherein you are still fetching messages from the queue in one by one fashion, or maybe in small micro batches, but then now you have some power of multi-processing involved, so you can do much better than the single process consumer, and then go for storage. The issue with multi-process consumer is also same that is with single process consumer, that if your data source is producing messages at a very fast rate that your multi-process consumer can't handle, then you start to have lags in the queue, and the entire system goes slower. Now the complexity with multi-process is obviously there, because writing a multi-process, multi-threaded program itself is complex. There are so many nuances between inter-process communications that needs to be taken care of. And yes, if you want to scale it out horizontally by trying to run it on multiple nodes, then that is not a very easy way to go about it. So the biggest improvement that happened on top of multiprocessing was the introduction of Mapreduce framework. It's a framework that works very much like divide and conquer, and the fundamental idea isn't so different from the multiprocess consumer. What happens is that you take data and then you split this data into different, let's call them sets, and these sets are then individually worked by different processes, and once they produce some intermediate result, then these intermediate results are reduced together to form your final result. And Hadoop MapReduce was a very popular engine that implemented MapReduce at a grand scale, and you could create a cluster consisting of hundreds of thousands of nodes and can perform any data processing that you want to do. Now in this example, we are taking a look at a scenario where the business use case is to find out the count of words in a text. And let's say here is your input, which contains a couple of words. Now what happens is that you split this input. So let's say we split this input on the new line character, and we can see that deer, bear, river are the first sentence. The second one is car, river, because there's a new line after river in the first and second sentence. So that's how we have split this up. And now this splitting can again be mapped, wherein you further split this sentence based on, let's say, white spaces. So now you have deer, bear and river which are mapped out. And when you are creating this map, because we know that the end goal is to count the number of words, you simply add one in front of every word that you encounter. And in front of is more a visual way to put it up, but actually you create some sort of a list or a set that contains a key value. So your key is going to be deer and your value is going to be 1, and so on. It happens. So in the mapping stage, as you can see, all these sentences are divided into words or tokens, as sometimes we call them, and they all have 1, which is the count associated with them. Then there is a shuffling step that happens, and in this step basically the output from mapping stage is shuffled so that you have a key that is still your unique key, because that's what we want, but your list now becomes your value now becomes a list that contains as many elements as the number of times it was observed in the mapping phase. So that's what happens in shuffle phase. And as we can see that in front of bear there is 2 ones, and in front of car there is 3 ones. And in the final reduce phase, what happens is that you take that list and you sum up all the elements of the list in order to get the final count that is associated with every word, which is what happens in the reduce phase. And then your final result is available, which is a list of again a key value pair, wherein the key is your original key, which was the tokens or the words, and your value is the absolute count of times that it has been seen in the given data set. So this is a broad overview of MapReduce and how it works. Now this was great. Like when MapReduce came out, it was able to solve a lot of problems that people were struggling with earlier, but there were some clear downsides of MapReduce as people tried to use it for more advanced use cases. The first one was that it's difficult to program MapReduce directly in a Hadoop MapReduce environment, and there are certain performance bottlenecks, and especially when it comes to machine learning algorithms, wherein there's a lot of iterative jobs happening, it wasn't able to put the right kind of performance and speed as was required. And That's where Apache Spark comes into picture. Apache Spark is a data engineering, data science, and ML execution engine, which fundamentally has the similar concept of Mapreduce, but it changes some things drastically, which gives a lot of performance gain on top of Mapreduce. And we'll discuss some of those performance gains. So Apache Spark can work with batch and stream processing both. Some of its features are near real-time data pipeline. So you can extract data from any data source in a near real-time manner, be it a store like HDFS or some other file system, or be it any messaging queue like Kafka or something else. It also has near real-time processing, so your results can be near real-time. You are able to achieve a good processing speed. There's in-memory compute. So what happens in Apache Spark is that it scans your HDD only once, and then it keeps on scanning the memory, which means that it's much more efficient. Now, this was very different in Hadoop Mapreduce, because there was a lot of disk IO that was involved in similar processing. So if you compare the disk IO that happens in Hadoop Mapreduce versus Apache Spark, you'll see Apache Spark is a clear winner by a factor of at least 3 or more. There is again flexibility, because Apache Spark has support for many different languages, and you can choose your favorite language to start programming on it, and necessarily you don't need to learn a new language to do it. So it's in Java, there's Python, there's Scala, there's R, and it's fault tolerance, which means that RDDs, which are the most fundamental unit of representing data in Apache Spark. So RDDs are designed to manage failure or any worker node in the cluster. So that gives fault tolerance, and there is a lazy evaluation in Spark, which means that it is the job is optimized even before it is executed, which reduces complexity and increases speed, and it also saves computation. So these are some features that Spark offer us. Now, the core abstractions in Spark are RDDs and DAG. RDDs are resilient distributed data set. So they are immutable and partitioned collection of records that operate in parallel. So taking an example from here, you can think of the splitting part creating the Deer Bear River as equivalent to RDD. It's not exactly same because it's a different engine, but just for understanding, we can say that this is an RDD. And RDDs can be created by reading from a data source like HDFS or HBase, or they can be created by applying some transformation on an existing RDD. The other abstraction is a DAG, directed acyclic graph. So DAGs are the way in which Spark plans out what execution needs to happen at what stage of the entire application. And this is where the whole idea of lazy evaluation comes into picture, because it can optimize your operation by understanding the dependencies between different nodes in this DAG, and they can be evaluated lazily, they can be loaded lazily, and it really helps in optimizing Spark. So RDDs there are two classes of operations that you can perform with RDDs. There's transformations and there's action. So transformations are the operation class that essentially convert one RDD into another. So for example, if you want to take an RDD and let's say multiply that entire RDD by something else, that's going to be a transformation. Action are the operations that actually produce a result as a so when they are applied on an RDD, they don't create another RDD, but they create a a final result that can be used. Now, along with RDD, there are certain metadata that is associated with them. For example, what are the partitions, what are the dependencies of this RDD, what are the compute functions that are needed to be applied on this RDD, preferred locations where this RDD can be sent for execution and partitioner, and so on. The DAGs, right? So DAGs are the sequence of computations which is performed on data in the context of Spark. And in this DAG, the nodes are the RDD partition, and the edges are the transformations that are to be applied on top of data. And this DAG is acyclic, meaning that you cannot return to an older partition, you cannot return to an older state that has already been performed. And this is a direct transformation, which is an action that transitions data partition state. Now again, let's look at the same example that we talked about in a different context of Apache Spark. So in this couple of lines, there's not a complete example. There are a few more lines that needs to be added on top, and so on. But this is the really the core of it. So as you can see in line number 4, it's reading a file and it's creating an RDD out of it, which is then applied some transformation, and then it's finally reduced, creating the word count. And if you look at this diagram here, that's when RDDs are created after reading from HDFS, and every operation, for example flat map or map, transforms this RDD into a different RDD, unless they are until they are finally went by reduce by key, which also creates an RDD, and then for each, which also happens on RDD. So there's RDDs all the way down in Apache Spark. And if you have to write this same function in Hadoop Mapreduce, it's going to be a much longer function than just a few lines that happens in Apache Spark. Now this is an overall architecture of Apache Spark cluster. So in a Spark cluster, there are typically two kinds of nodes. There's a driver node and then there's a worker node. The driver node is responsible for driving the entire execution. It's the one that creates the Spark context, and Spark context is really the entry point of any Spark application. So before a Spark application can initiate, it needs to create the context here, and this context is created by providing certain configurations as a part of parameters to the Spark context function in the Spark APIs. So right, so it allows a Spark app to spin up a cluster with the help of a resource manager. What happens in creating of the Spark context is that there is a config, for example, how many number of worker nodes are required, what is the memory size, how many cores, etc. And what this Spark context does is that it gets the status of the application, it sets config, it's canceling jobs, cleaning, dynamic allocation, and every core that needs to be performed during the execution life cycle is something that is done by Spark context. And then there are worker nodes. Now worker nodes are the ones that are responsible for actually executing that unit of task, and inside each worker node are one or many executor, and these executor, think of them as a distributed agent. We start them at the start of Spark application, and then it runs for the lifetime of that app, and this is called a static allocation of executor. There is also a dynamic allocation of executor, wherein the number of executors changes dynamically depending on load and other factors. But these are the two ways in which executors can be spinned up. They take tasks, they execute, and they return the result to the driver. And they are also responsible for in-memory storage of RDDs, and that's where the caching comes into picture, so that the data is readily available, and you don't need to perform a disk IO in order to get those data points. And this is the Apache Spark ecosystem. So there is a core set of APIs for structured and unstructured data, and these APIs are available in Scala, Python, Java, R. You can use whatever language you want. At the fundamental of this core API is a compute engine which does all the memory management, task scheduling, fault recovery, and cluster management. There is a cluster resource manager. So Yarn or Mesos are some of the popular resource managers that are used. You can also run Spark in a standalone mode. For example, if you want to just perform a quick experiment on your laptop or desktop, you can definitely run Spark in a single or a standalone mode. And once you are ready to actually deploy it on a large scale production environment, that's when you need some sort of a cluster manager. Yarn is very popular, and that helps allocate resources to different nodes in the cluster. And at the bottom is a distributed storage, which may be required, may not be required at times. Excuse me. Right, and at the top, what you are seeing, these four boxes consisting of Spark SQL, streaming, MLlib, and graphics. These are the libraries and APIs that extend the core functionality of Spark by doing different things. For example, Spark SQL provides native support for SQL in RDDs or on external data source like JDBC or JSON. So you have one unified way of querying data from whatever data structure that you are using in your Spark application. Spark Streaming is the scalable, fault-tolerant stream processing engine, which supports both batch processing and stream processing. Graphics is the most latest addition in the Spark API, and it extends the Spark RDD by introducing a new graph abstraction. So this is very useful for any graph processing that you want to perform. And MLlib is the machine learning library that Spark offers, and it's a scalable machine learning library, and it provides tools like for example, ML algorithms. There are a lot of common algorithms that are implemented and exposed as API. So your classification, regression, clustering, some of the most common algorithms are already there. There's a featureization, wherein feature extraction, transformation, dimensionality reduction operations are present. It also provides a way for you to build complex machine learning pipelines, because very rarely you will have a machine learning application that is very simple and has only one, let's say, model or processing involved. In all practical purposes, you will have multiple types of models and data preparation, data cleaning, post-processing stages involved in an actual production pipeline. And then definitely there are certain utilities for linear algebra, static data handling, etc. Now the main concepts in Apache Spark MLlib is data frame, which is really an abstraction built on top of RDDs. It's a flexible data type from Spark SQL that allows parallelism. There are transformers and feature extractors. So for example, you will have tokenizers, PCA, normalizer, discrete cosine transformer kind of transformers available right out of the box for you to use it. Feature extractors like TF-IDF, word to vector are also present. Then there are estimators, which are the ML algos that can be fitted on a model, fitted on a data frame that returns a model. So for example, logistic regression is an API that is provided by Spark MLlib, and that is an example of an estimator. Spark uses a uniform API to define all the parameters along with its documentation, and that's where the parameter concept comes into picture. And pipeline, like I mentioned, it's just a chain of transformers and estimators. So the way these APIs are designed in Spark, it's very easy for you to use any estimator, any transformer, and you can chain all of them to create a really complex pipeline. And that's what that's what is your actual production level Spark machine learning application. Now, this is not only limited to standard or classical machine learning. There's deep learning available in Spark as well, and these are some of the top libraries that are used for doing deep learning on Spark. Now, the reason why we went so much into Spark is that because Spark is really popular. It's the amount of development that is happening on Spark, the community, the energy around Apache Spark, it's just huge. And for any machine learning production ready application that you want to build, Apache Spark should be one of the top 3, if not top 5 choices that you should definitely consider.